yeah, it's been a pleasure being here. Just to check, does this, I think I'm on. Everyone hear me okay? Okay, cool. Sounds good. I'm kind of loud anyways, so who knows if we need the mic. But yeah, thank you, Gita, for that very kind introduction. And of course, it's been such a pleasure meeting with so many folks today. So thank you for spending your time with me. Yeah, my first love was actually paleoclimate and kind of some geology stuff. So even though I do more modern day computational climate science today, I really love visiting kind of earth science departments and having those conversations. So it's been such a pleasure. Today I'm going to talk specifically about heat extremes, and you as in Texas I think are very familiar with them, and my title here, we've seemed to see so many record-breaking heat waves. Can we really use our understanding of climate science, some statistics to understand what's going on, is it what we expect, what are our climate models showing, and why are we getting so many of these heat waves? So I'll be talking about trends and drivers of summertime heat extremes. So this first plot will surprise probably no one, but I just want to highlight one thing in particular. So we live, as of course we all know, during a time of rapid global warming at the moment. But what this plot highlights really nicely is that rapid global warming is happening much more quickly over land than over ocean. So we often just see one of these plots of going from, say, 1850 to near present of global mean temperature anomalies. But here it's been divided into ocean average temperatures in blue and land average temperatures in red. And what you can see, just eyeballing this plot, is land temperatures are warming much faster, especially since, say, 1970 or so. Theory and some observations suggest about 60% faster. This is even a little bit more. You can think about, kind of a 60 to 70% increase in land temperatures compared to ocean temperatures, which of course also dominate that global mean temperature change. And as a result, the response of global mean and global land temperatures warming is, of course, that we are getting a lot of heat waves. And so I could have pulled this for basically any month, but NOAA does, or at least used to, make these significant climate anomaly and event plots. So this is from last summer, August 2024. And basically everywhere you see a thermometer on this picture, which is happening actually both in the northern hemisphere summer and the southern hemisphere winter, is a place where the major kind of weather event or weather anomaly of this month was a heat event. And you can see that really around the globe we're having these kind of notable heat events on a very regular basis. So all of these changes have really motivated a lot of my work to understand the heat waves that we're observing and that we're simulating in our climate models. And today I want to share with you 3 pieces of work about heat. The first is on a specific heat wave, the 2021 Pacific Northwest heat wave, which people might remember as a somewhat recent major event, but I'll remind you as well. The second is looking beyond the Pacific Northwest, more broadly about how changes in the tails of summertime temperature, how they have changed, how they will change in the future, and connections to land-atmosphere interactions. And then third, we're going to loop in humidity and talk actually about the drying of the dry, so decreases in humidity on already hot, dry days. So not so much the hot, humid days that you have here in Texas, but the kind of hot, dry days that we get more in the western U.S. My plan is actually to pause briefly between each of these sections if there are kind of questions that come up specific to one of them. So happy to kind of intersperse questions over the top in that sense. Okay. So I just want to begin with this 2021 Pacific Northwest heat wave study, and I want to take everyone's brain back to 2021. Actually, I'm just curious, would you raise your hand if you remember this heat wave? Okay, and then was anyone in this heat wave? Okay, I often get like 1 or 2 even in smaller audiences. Wait, did you have your hand up, Gita?
I was not in it, but I remember.
Oh, you remember it. Okay, got it. So as a reminder, this was just this kind of record-shattering heat wave. What's shown in a map here, just to look at, there's no color bar, but just to get an idea of the spatial pattern of this heat wave. There's this major heat wave. As Americans, I think we mostly heard about it in Washington and Oregon, but really the center of the heat wave is more in British Columbia and Canada. Notably, for instance, a weather station here measured around 50 degrees Celsius temperature anomalies and then burned down because of wildfires associated with the heat. And if you think about the summertime climate of the Pacific Northwest, we tend to think of it as kind of a mild climate, but for instance, Portland, Oregon observed, I think, 115 degrees Fahrenheit at their airport. And so it just seemed totally out of nowhere. Just to look at this in a time series sense, The red, this is showing June 5th, and then this heat wave peaked around June 30th over here. The red is showing from ERA 5, the temperature is in kind of the center of the heat wave, so major heat wave peak here. But notably, if you can see this kind of lighter gray shading in the background, this was a historical maximum and minimum. And so this heat wave broke prior records on the order of 5 or 6 degrees Celsius, depending on where you were. So hopefully all those metrics will make you realize that this heat wave just seemed to be totally out of nowhere. So based on my prior work, which a lot of it has looked at and will look at and talk about later in the talk today, how summer temperature distributions are changing, the first question I had is, okay, the Pacific Northwest has warmed by, say, a 1.5 degrees Celsius or so since around 1960. But do we see historical evidence that these hot days are really warming faster than the median or the mean? So is this kind of, did we expect this heat wave? Do we see evidence of those hot days? There's some process where they're warming more. And the answer to that was basically no. So what's shown here is data. This is from ERA 5, just because it's easier to look at in a talk. In our paper on this, we looked at long-term in situ observations and did more of a careful statistical analysis that I'll show here. But just for the sake of the talk, this is ERA 5 temperature data from 59. I'm stopping here in 2020 before our heat wave. Each one of these dots is a daily maximum temperature value for that summer, looking at 30 days centered around this heat wave, so June 15th to July 15th. And this red is basically a trend in the median temperature over time. Because of how we kind of stretch this plot, as you can't really see this is going up, but it is. This region is getting warmer. But importantly, if you eyeball this, and this is true statistically, the hot days don't seem to be getting warmer any faster than the median. So it seems like we're seeing kind of sometimes called the vanilla climate change signal. Everything's getting warmer, but more or less the distribution of temperature is staying the same. Or in other words, your hottest days are warming at the same pace as your average days. But then, we went forward to 2021, which I've added here at the end of the plot here. These are those 30 days during 2021. And again, they just seem to be totally out of nowhere. All of a sudden, we had this huge jump in these hottest days that seemed totally unprecedented and unpredictable based on those prior observations. So the question that we had in this paper is, how can we understand the probability of these events given that we haven't really seen this historical amplification of heat extremes? Or in other words, how can we understand or quantify a probability of these unusual temperatures after accounting for that climate change signal in the middle of the distribution, but trying to understand the magnitude of these very extreme events? And just to again put you back in kind of the mindset of 2021 and 2022 after these events had happened, we as a community were actually collectively struggling to find a probability greater than 0 for these events happening. So some people had fit kind of some standard statistical models for extreme events and found that the probability of these occurring was 0. Other people had looked in climate model large ensembles to try to find an analog to these events and really could not find things in climate models. And so we kind of set our bar low. We just said, can we understand the reasons why these events could happen with a probability greater than 0? So our first hint, and I'm sorry for those of you who did not want to think about statistics in this talk, but we're going to use a few stat words at the moment. Our first hint of what was going on is that many weather stations in the Pacific Northwest region have what are called positively skewed temperature distributions. So this is an example of a positively skewed distribution here on the right. And all that really matters is that the positive skew means that these extreme events on the right-hand tail are more likely than you would expect if temperatures were, say, normally distributed or had a Gaussian distribution. I'm showing that here in a map form on the left-hand side. So just to contextualize, here's Oregon and Washington and British Columbia. We defined our domain of study with this box kind of centered on the heat wave. And each one of these dots is a station with relatively long-term temperature measurements, in most cases going back to 1920 or earlier, although these stations up in the up in northern British Columbia and tended to be shorter records. Any station here that has one of these brown colors is a place where the skewness was found to be positive historically. So before we had this heat wave actually occurring, these stations had distributions that were kind of like this, meaning that they tended to be mild in their climate overall, but every once in a while they would get these anomalously large heat wave events. And so historically they'd be more in the order of 100 degrees Fahrenheit, not 115, but nevertheless you do get these major heat waves in these regions. Sorry, I have a little bit of delay, I think, when I click this thing. There we go. So the next thing that we did is we looked at the spatial pattern and we compared it here to how large the heat wave was during 2021. And this is in sigma units, so think about that we're normalizing by the variance and just thinking about an event as being a 1 standard deviation or 2 standard deviation events. And if you look at these two maps, you can see they look pretty similar in their patterns, with like the deeper reds corresponding with deeper oranges. I plotted them here against each other, and you indeed see a relatively strong relationship between places where before the event the skewness tended to be positive, having larger temperature anomalies. So I want to kind of back out of the statistics right now and think about a reasonable physical interpretation here, which is that when you have these positively skewed distributions, what it tends to mean is that you have multiple processes coming together that can lead to an anomalously high temperature. So in this region in particular, like in many regions, heat waves are associated with, of course, clear skies, a lot of solar radiation reaching the surface. But in addition, this region is just downslope of some mountains and kind of a hotter inland region that's not so coastal. And so when you had this major heat wave in 2021, you really had a convergence of events. You had these sunny skies, your solar radiation coming down, but you also had winds coming down the mountain. So you had adiabatic warming, these winds coming down the mountain, also bringing in warm inland air to the region. And so you can think about these positively skewed locations as places where you tend to have the convergence of different processes that then lead to these occasional more extreme type of events. And I think that's why you see the mapping between these two, is that it's indicating that similar processes occurred during this 2021 events. So this is kind of our first hint, is that we said, okay, this region is actually not homogeneous. Each of these locations has a particular temperature distribution, which indicates the certain processes that control its temperature and its heat extremes. And we see that manifesting in how large the heat waves were in 2021. But we wanted to make sure this was not just something weird with kind of a small data set focusing specific on this one region. And so we then turned to one of our climate models, CESM2, and kind of played the same game, but looking all across the mid-latitude land masses. So things that are kind of a similar latitude to the Pacific Northwest, where we'd expect similar processes to cause heat, but looking over the whole domain. So let me walk you through this plot. It's a little bit complicated. On the left-hand side, on the x-axis, we still have skewness. That's what I talked about before. Again, the one thing to remember is that positive skew means that you're more likely to have those more extreme events. The y-axis here is a metric called kurtosis. All that matters for you to know is that a positive kurtosis, again, means you're more likely to have extreme events. And then the color is showing in the climate model the hottest events that happened over 8,500 years of model simulations. And we're looking only at internal variability. We've removed the climate change signal to get these 8,500 years. So for those who might work with climate models, we used a large ensemble, removed the ensemble mean, and looked at the internal variability over all the ensemble members and all the historical years. And what you can see in this plot is similar to what we found in the other plot, although we now added this second dimension, where when you have places that have climatologically or on average a positive skewness and kurtosis, their 1 in 8,500 year event can be huge. It could be a 5 sigma type of event. Whereas when you look at places that have negative skewness and negative kurtosis, their 1 in 8,500 year event might be less than a 3 sigma event. Not that unusual in a way, or seemingly not that unusual, but in that case occurred again only once every 8,500 years. So if we add the Pacific Northwest stations to this plot, we can see that they're now showing these bigger dots with the black outline. We can see that more or less the colors align with each other. So again, these stations that basically had these very, very large anomalies during the events, they tended to have positive skew and positive kurtosis. And if we look at similar locations in CESM2, our climate model, that share those same statistics and perhaps those same physics, we see that they can also produce those large events. And so this helped answer the question of why people hadn't found these events in climate models before. One, we had to look at the biggest event across 8,500 years of data to find an equivalent event in the climate model. So the climate model does produce an event as extreme as this Pacific Northwest event, but they're very, very unusual. And the other thing is that we kind of had this idea of looking at this analog space. So instead of trying to say, does the climate model in this same region produce these events, we said, let's look at locations that share the same statistics and therefore potentially the same physics and see if they produce these events. And indeed, we see that. So we kind of put a back of the envelope number. This is roughly kind of a 1 in 10,000 year event. Don't put too much focus on that number. There's a lot of caveats. But the important point is we could demonstrate that these are kind of possible in climate model world. We have a non-zero probability for this event occurring. And this should give you some intuition. I just want to show you what these events look like in the climate model, just to show you that they really do seem equally unexpected to what we see in what we saw in the observations. So this is just pulling out one grid box. It does happen to be in Central Oregon in CESM2. And this is pulling out the single ensemble member that had one of these very, very large events. What's plotted here from 1850 to I think 2024 is for that kind of early summer season that the heat wave occurred, the seasonal maximum temperature. And so this is the hottest temperature each year basically going forward. And you can see that nothing really much happens in the climate model, and then kind of out of the blue, you get this ginormous event that is comparable to what we saw in the observations. And so what it's showing is that our climate system, even encapsulated with our climate models, can have these very, very long tails that we may not anticipate with a historical record. So we need to be pretty smart as we think about how extreme can the climate system be, even without climate change. This is all about internal variability. We kind of removed climate change from the story here. Even with internal variability, our climate system can produce these very large, unanticipated extremes, such as what we saw in the Pacific Northwest. So our main conclusion from this study, which we demonstrate in this is just a schematic to be clear, as someone in a previous talk thought this was actual data. But if you think about this blue distribution as kind of a positively skewed long tail distribution that's more like the historical climate or some past climate, what we're doing is we are moving this towards warmer temperatures, towards this red distribution. And that is the climate change signal. We accounted for that as kind of a pre-processing step in our modeling. But what this event that we observed was basically, partly that shift of the distribution, but largely that we just happened to sample something at the very tail of this distribution, and that led to the very extreme event that we had. So our belief is this is mostly kind of a shift in temperature, plus basically the bad luck that produced that weather of that event. Okay, I'm going to briefly pause there in case anyone has any questions, clarifying or otherwise. Yeah, go ahead.
So my question is that when considering those distributions, were those distributions for extreme events only, were they like extreme value distribution, or they were for the whole trend of the?
Yeah, that's a great question. We're not using extreme value distributions here. In fact, in this paper, we demonstrate why maybe you shouldn't use extreme value distributions. I'll talk about that in 1 second. But yeah, we're considering the distributions across summertime days, or in this case, it's early summer, June 15th to July 15th. But thinking about within season distributions and how are those shifting. So within it over time, is kind of across days, we're obviously getting warmer, but is anything changing in the shape? How are we doing these very extreme events? But the distributions are not specifically the extremes. I'll just briefly mention on the GEV. So the statistical model that people fit early on when they said this has a probability of 0 was, as you might expect, a GEV. We in this paper actually went through and demonstrated that it's actually super common because you can play with climatology of all this data. So you can actually demonstrate that it's really common that if you kind of have some extreme event and look at, say, the 70 years before, that you would estimate that event had a probability of 0. So I think that everyone needs kind of a cautionary tale if they want to use GEVs in climate data, because climate data violate every assumption of GEVs immediately, and knowing how those violations could impact the results is really important. Yeah.
I know the focus on the land, but how do the ocean figures nearby the so-called law consequences? How would that machine
I'm embarrassed to say that I cannot answer that question because I was focused on the land so much, and I often use in situ data on the land. So the actual paper totally uses weather station data. I just showed the reanalysis here kind of for illustration. But certainly you often do have, of course, co-located ocean and land heat waves. And I think there's actually kind of an emerging new subfield within climate, people thinking about the interactions between them. Like, is it just that there's one common driver of a big high pressure system, or do you actually have kind of causal connections between them? So I don't have a good answer except to say I think it's an interesting question to think about. Yeah.
So in the figure that you were showing how the extreme heat days trended with, had the same trend line, I guess, as the average temperature, so they weren't, other than this anomaly, it wasn't necessarily increasing at a greater rate overall.
Correct, yeah.
Was that specific to that region, or did you do any sort of comparison to other regions that maybe that would be like the answer is specific?
So glad you asked that question. Now stop with the questions because that is our next section. Is basically, yeah, in this region we saw that we don't see this amplification of the extremes, but what about other regions? So let's take a look at that. Oh, sorry, one more, yeah.
Sorry, just a quick one.
Yeah.
I know you focus on the past 8,000 moments. Basically, I think this maybe cause politics policy. More than if we could look at if we could do the model and look at the past several weeks, all the war not forced, no. Also, use more statements
I think that's another great question that I can't answer, but I do think that looking into paleo and as much as we can learn about extreme paleo or from model simulations is a really exciting direction. So if you want to collaborate on that, let's talk more.
Yes, we said
Awesome. Okay, so in our next section, what we're going to talk about is exactly what was asked before of do we see in other regions of the world, do we see any kind of general move towards heat extremes warming faster than the median? And I'll just tell you a quick anecdote to motivate this. So I actually published a paper at the end of my PhD that kind of tried to answer that question, but it was 2016. I and the community have learned more since then, and so I thought it was worth revisiting, not only because we had new methods and new ideas, but also because, like all of you, I have experienced heat waves that seemed very, very hot. And the conclusion we drew in 2016 was that more or less heat extremes are following the median. And I started to get nervous that if I told people this too much, that it no longer was true based on the extremes that we observed in 2021, 2022, 2023. It just seemed like every year was kind of a new level of extreme heat. So I wanted to revisit it with all of our kind of new knowledge and try to answer that question again. So the question we're going to try to answer is, at large scales, are heat extremes warming faster than typical summertime temperatures? And then we're also going to use some land-atmosphere interaction theory to develop some physics to understand the results. So I won't tell you the answer yet, but we will find out. Okay, so another motivator besides my experience of extreme heat was that, of course, in the literature, people have proposed various mechanisms that would suggest that hot days kind of warm preferentially faster. And so I just pulled out examples. There's more papers than just these examples. I just pulled out a few examples here. So Mike Byrne had a nice piece of work in 2021 where he said in the tropics, hotter days, which kind of live up here in this plot, warm more, and he argued it was physically because they are drier. This plot, which will be important later, is made entirely of either future simulations with CMIP or like 4 times CO2 simulations. They're the future, basically, not the present. Suchin Dwan, she was my postdoc, this is before she joined my group, argued similarly in the tropics that hotter days warm more than average days because they dry more. So this plot basically shows changes in latent heat flux on your hottest days compared to your average days. Latent heat flux, for those who haven't heard of it before, is basically the energy that goes into evaporating water. And so if you have a drier surface, there's less water to evaporate. More of that incoming energy will typically go into increasing temperatures. We tried to actually unify these two ideas in a recent paper, so that was kind of a fun thing. They are somewhat unified. And then in the mid-latitudes, there's been a few papers, but here's one example, led by Mike Mann, and it argues that hotter days warm more than average days because these high amplitude quasi-stationary waves, which are shown in this plot, are becoming more common, perhaps due to polar amplification, although this is debated somewhat in the literature. So there were kind of ideas, mostly, especially in these other two cases, using climate models, simulating the future climates. This one based a little bit on observations, but there are these ideas that hot days are warming or could warm more than the average. And so I'm someone who at the end of the day, I like to look at the observations, and so I basically just had the simple question of, do the data support hot day amplification? And by that, when I mean hot day amplification, I mean hot days warming faster than, I'm going to use the median here, so I know it sounds weird, but basically I do hot days warm faster than the median or 50th percentile of days. My signal must be right here. There we go. Okay, I'm not going to go into all the methods here because it just is not the most interesting part of the talk. So I just briefly have this little box saying how we're going to do this. What we're going to do is look at trends in the ranks of the difference between, in any year, a seasonal extreme. So think about like the hottest summertime temperature in a year, minus the median. And our typical metric of the extremes is going to be either the hottest, or you'll see also the coldest summertime day. The reason we're looking at ranks is because of the differences in temperature distributions spatially. We want to be able to ultimately do some spatial averaging and things get complicated, things have different distributions. Happy to talk about it more if anyone's interested, but looking at ranks basically allows us to instead use the same distribution in any location in space. So all you need to think about is, with this metric, a high rank means that you have a large difference between the hottest temperature and the median temperature of that year. A low rank means the opposite. So if you think about over time, imagine your temperature distribution is widening. I don't know which way this looks good for you guys, but if it's widening over time, so your hottest extremes are getting hotter than your average temperatures, your ranks would increase over time. So positive value of what I'll show means that hotter days are getting hotter faster than typical days, and a negative value would be the reverse. In this case, because we wanted to look globally, I am going to use the ERA5 reanalysis, always looking at daily maximum temperature. We looked 1959 to 2023. Before 1959, things get a little wonky with ERA5 temperatures in our experience, so that's why we don't go back earlier. And then when possible, we compared with station data and another data set called CHERTS, just to kind of sanity check this, since ERA5 is a reanalysis, of course have issues, and not be fully representative of reality. Okay, so this is the plot of those rank trends, looking at comparing the hottest summer day to the median summer day. We're looking at summers defined as a function of latitude based on when you have the hottest 60 days, or maybe the hottest 90 days. Hottest 90 days, I think, during the year. So, like, no matter where you are in latitude here, this is always the hottest period of the year. As I mentioned, red, which is a positive value, are any places where, in general, the hottest summer days are warming faster than the middle. And blue is the opposite, it will be warming less fast. But critically, even though you see lots of colors on this plot, I want to highlight these white contours. There's very few of them. You probably can't even pull them out. But these are the only places where we identified that trend as actually being significant. So, of course, we sample internal variability, we sample data. There's often going to be a non-zero trend. But basically everywhere around the globe, including, for instance, this Texas area that we're in now that tends to be red, we generally found that these trends were not significant. In other words, when you looked at a local level, it would seem to be overall true that the hottest days were warming at the same pace as those median days. So we already kind of knew this would be the case because the signal was already expected to be small based on prior work. The reason that we did this whole process is because we wanted to average. So we know in climate or earth science, things are often noisy locally, and one of our tools that we use is we average stuff so we can see a signal emerge. The reason we went through all this rank stuff is that it makes the averaging statistically simpler. And so we basically took this map and said, okay, there's nothing really happening locally, but what happens if we average across space? And we're going to be looking across the globe, the northern hemisphere, the deep tropics, and the southern hemisphere as our different domains. So it probably is not a surprise if you eyeball this, which probably has equal red and blue values on it, that when we averaged across these spatial domains, there basically was no significant trend at any of these scales. So what's shown here, we have the year on the x-axis, 59 to 2023. If you just focus on one of these, say the global one, each one of these points is the global average of the ranks for that year, and then northern hemisphere, tropical, and southern hemisphere. The gray shading, if you can see that there, is what you would expect from just kind of a null hypothesis of no trends. And then the purple is the actual fitted trend to that data. And so you can see in all of our domains, the purple line is basically within the gray shading, meaning that we don't identify any significant trends in this metric. Again, since this is a little abstracted, the important thing to remember is that positive trends means that the hottest days are warming faster than the median days. So what this is saying is that all of these scales, the hottest days are basically following the median. So that was kind of interesting, and basically said that our prior work still seemed to be true despite these recent hot years. And so we asked ourselves, okay, the temperature distributions in the summer, they're not just about those hot days. What about the other side? What's happening with our colder summer days? But we're still using daily maximum temperature, so we're not talking minimums here. So still daily maximum, but our cold summertime days, how are they warming compared to the median? And in this map, you can immediately pull out that there's more blue, and there's also some more of this kind of white stippled area. So overall, what we see, and this is also shown in the spatial averages, you can get it. Is it good to up on me? All right, I'll just have to walk across. There we go. Is that there tends to be in all of our domains actually significant trends towards damped warming of the lower tail. So if you think about your temperature distribution, our hottest days are following the middle of the distribution, but our colder days are actually getting stretched out a little bit. Now, this asymmetry is actually pretty important in the field of heat extremes and temperature changes. People often just quantify changes in temperature distributions by changes in the mean and then the variance. The variance is a symmetric measure of changes in total tails, and you might interpret that an increase in variance as kind of a faster increase in heat extremes. But here we see that really when there are increases in variance, it's actually largely due to this kind of stretching of the cold tail that is still warming, but not warming as quickly as the warm tail. Okay, so we wanted to understand why. First we wanted to challenge talking before my slide pops up. First we wanted to understand what the climate models are doing, what our observations are doing. And so we looked across, some hundred number of climate models, simulations across something like 26 climate models. The alphabet soup for those who work with CNET 6 models is down here. I don't expect you to kind of read any one of these model names. But basically on the x-axis here are all of our climate models that have the relevant data in CNET 6. On the y-axis, let's look at the global one here first to start, is the trend in range. So basically the same thing I showed you on the prior plot. Each one of these black dots is a single ensemble member. If there's multiple ensemble members, the red is the ensemble mean, or it just goes on top of the black if there's only one ensemble member. The purple is what we've observed, so that's basically the trend of the plots I showed you before. The green is the multi-model ensemble mean, so the average across all of the red dots. And then the gray is, again, kind of the null hypothesis. So somewhat surprisingly, the multi-model ensemble mean agrees almost perfectly with the observations across all of these domains. But the main thing is that climate models agree with the observations on a historical lack of hot day amplification. Now, I was kind of surprised at this. Actually, climate models, of course, have a lot of issues, but this does not appear to be one of them. So the climate models agree with the observations that the hottest days are warming at the same pace as the median. All right, I'm going to have to give up on my clicker here. However, when you look at that cold tail instead, we actually see that disagreement emerges. And so the same stuff is shown here. I'm just going to move this to the other side since I'll be facing the other way. The same information is shown here, but now looking at the trends in that cold tail stretching. So if you remember in the observations in purple, our cold tail was basically warming less quickly than the median. So we see it as a negative value here. But our climate models all happily say that the cold tail should be warming at the same pace as the median. So we had agreement on that hot tail stuff, but pretty large and substantial disagreement on the cold tail. I won't go into it now for the sake of time, but we actually mapped the observational source of these cold tail stretching to precipitation trends, some of which may not be properly simulated in climate models, but I think there's still some more work to be done to answer quite what is going on here. And then I just wanted to add this slide for future. So everything we've looked at so far has been historical to use observations. But this is now looking just at climate models for what's happening in the future. And I'll just highlight this one here. This is our tropical average. And what you can see is that in the future, at least based on the SSP 370 scenario, climate models do suggest that there's going to be a significant amplification of heat extremes in the tropics. This is, of course, a region that is already hot, so the fact that you're going to see amplification there is somewhat concerning. But there's a huge amount of spread across the climate model, so I think it would still be important to understand why the climate models kind of agree on the signal overall, but disagree in a pretty substantial way in terms of its magnitude. And this signal, by the way, is I just want to emphasize the mapping to the prior work before. So that Byrne paper I showed before, the Dwan paper, they were all looking at future scenarios. So we do agree with them in our method that in the future, tropical amplification will emerge, but historically it has not, which is pretty interesting. Okay, so we then wanted to understand, beyond these trends, can we make some basic physical model for what is happening with why and how heat extremes are changing or are not changing compared to the median? So one thing I've been having a lot of fun with recently is learning all about land-atmosphere interactions. It's kind of a new and emerging direction in my research group. And some of the basics of land-atmosphere interactions are relatively simple equations, but I found they actually can tell you a lot of interesting things that are unexpected. So I'm going to walk you through not kind of a total derivation, but just a few equations that we'll put together to make some predictions and test some predictions for relative changes in heat compared to average summertime temperatures. So near-surface air temperature responds to land-atmosphere fluxes, which are themselves constrained by the surface energy balance. That's shown schematically here. Think about this as the land surface. We have short wave coming in, long wave going out, well, out and in both cases, and then the balance of these two, or net radiation, is largely partitioned between those latent heat fluxes related to evaporation and sensible heat fluxes, which increase temperature. You also have some ground heat fluxes which go into the ground but tend to be small. So you can write this balance out as a simple algebraic equation: short wave minus long wave equals latent heat plus sensible heat plus ground. And now that I'm closer, this works. Okay, cool. And what we've been wanting to do in a few different papers is basically play around with this balance and see if we can use it to make predictions about what temperature is doing. Now, that's not obvious how to do that because temperature is not in this equation, and in fact, these things are all fluxes, so if you've thought about similar stuff, these are all in units of watts per meter squared, whereas temperature is a state variable in units of Kelvin. But we basically made some assumptions, and other folks have done this as well. Here's a bunch of citations. That long wave anomalies, except for a trend related to greenhouse gases, sensible heat anomalies and ground heat flux anomalies scale with temperature. So that allows us to kind of make a move towards temperature. We combined that equation with the definition of something called the evaporative fraction. This is kind of a convenient metric to use in the context of land-atmosphere interactions because it tends to be a nonlinear function of soil moisture. So when you have dry conditions, it's low. As you increase your soil moisture, it tends to increase. And then when you have wet conditions, it's relatively constant. It's defined as your latent heat normalized by your net radiation, and is believed to have a relatively strong control on near surface air temperature. So I'm going to skip over a bunch of algebraic derivations. They're not too interesting for the sake of a talk. But basically, at the end of the day, by combining those two equations and making a few assumptions, we could actually write out an equation for temperature anomalies that says that they're proportional to two terms. One that is your change in forcing, which is defined as your change in shortwave, minus this long wave F basically means the amount of long wave that's linearly basically related to greenhouse gases, so increased long wave coming in due to greenhouse gases. So this forcing term normalized by this term that depends on your mean evaporative fraction, which is going to be spatially variable, minus the second term, which is a function of your evaporative fraction anomalies, scaled by your mean net radiation. So this is kind of a cool equation. These emerge whenever you have nonlinear equations in climate, where we have these two terms. Two parts of them are kind of anomaly terms, but the influence of those anomalies are scaled by the mean state. Okay, so then what we did, again, our goal is to understand does the land surface balance, land surface energy balance predict what's going on with temperature distributions. We then converted the T, or the temperature that we predicted by this balance equation, to those same ranks. So remember, we're looking at the seasonal extremes minus the median, and we're going to compare those with the observed ranks. Again, the nice thing about ranks is that this is only proportional to, so we're not predicting literally temperature, but we're predicting something proportional to it. Once we convert to ranks, we can actually intercompare quite easily. And to my surprise, this actually worked extremely well. So I'm just showing here, in my opinion, maybe you guys disagree, but I'm just showing you here one plot. I'm going to show you a bunch of them in a second. But this is looking at the ranks of those seasonal maximum minus median for the global average. The black and the purple are what you've seen before. So this is the global average year-to-year variation and trend in this rank metric. And then the blue and the gray are showing what's predicted by the surface energy balance model. Now, to be clear, this model has no tuning parameters. So just you're getting things about the evaporative fraction and the radiative forcing from, in this case, ERA5. Nothing is tuned. But it actually, both on an interannual basis and on the trend, predicted quite well what was happening with the relative trends in temperature in the extremes compared to the median. Now just adding, I just moved this one over here. I'm showing the same thing. Oh no. Oh, there it is. Okay. I'm showing the same thing here on the right for the cold tail, again for the global average. You can see the cold tail actually works even better for the interannual variability. Oh, all right, now it's not.
I'm sure something. That's the last one.
I know, it's like it's given up. Ready to go to summer.
Yeah, I have to reboot it, I think.
No worries. Well, that's coming up. I'll just say that the cold tail for both the interannual variability and the trend also is predicted quite well. And then if we look at basically, I know it's a lot of the same plot, but the northern hemisphere, the tropics of the southern hemisphere, we can see in all of our domains these surface energy balance arguments almost perfectly predict the relative changes in the hot extremes versus the cold extremes versus the median. So taking this kind of local framework actually seems to be relatively effective in predicting what's going on with our heat extremes. So just one last thing I'll say before we move on to the last section, and I'll take a few questions, is that I think this is a kind of a powerful framework, particularly for heat, because what it tells you is, in general, if you can predict what's going on with typical or median summertime temperatures, you can predict the extremes pretty well. And that's actually quite powerful because it's usually easier to understand what's happening with the median or the average than it is with the extremes. And so this gives you information about what's going on with the extremes based on that. I know I'm running already a quarter to, but I've taken questions along the way, so maybe it's okay. All right, are there any questions before? That was the longest section. The last one's not too long. Yeah, Keaton?
I have a question on this. So with the predictive skill of the surface energy balance framework, have you tested it for mean temperature, or does it have the same predictive skill with interannual variation, say in mean temperature, or is it uniquely good at predicting the extremes relative to the means?
That's a great question that I did not do because I was focused on this particular framing, but that would be great to check, and I can let you know. Yeah. Yeah.
So within, again, that framework, did you look at how that result would change at all in climate models, since the model, in some cases, especially with the maximum of the cooler, I guess, days, was off? I was wondering if that would have a different result if you were looking at climate models.
You guys are all giving me a great to-do list of things to do. Also didn't do that. But yeah, I know, it's a good question. Yeah.
So, correct me if I'm wrong, but based on what I understood, so we took the maximum temperature, minimum temperature, and the distance from the median and like the trend. So my question is that how could it change if we consider different quantities? For instance, instead of maximum and minimum, which would be very random, maybe we can like see the 90th quantity or 10% quantity, which will have like less variability, I believe. So
Yeah, so this one I can't answer. We didn't do exactly that, but I did explore various definitions of heat waves. So probably the one that actually is the best definition is if you do something like a 95th percentile cutoff and then add up the degree days over that cutoff, so it's kind of a cumulative metric of not only how hot are the heat waves, also how long are they. And because we're working in rank space, you can actually just like define any metric you want for heat and just run it through this whole process. And the results are basically identical in almost any way you define heat. And that, I think, is also a helpful result because people often argue in the heat wave community, how do you define heat? I'm going to define it this way, you define it that way, people go back and forth. And the nice thing about converting this to ranks is at least for this particular metric, we could show that the story is kind of the same no matter what. And I think that's pretty consistent with the fact that you're just shifting your temperatures towards warmer temperatures overall, and that manifests in these different definitions of heat. Yeah, because you're totally right, those maximum are kind of flashy. That's the one we focused on primarily, but yeah, you could do it with other things. Okay, our last section here is briefer, so don't worry too much about the time, hopefully, but we're going to briefly just bring in the humidity component. Historically, many people, myself included, have thought about temperature as kind of this univariate metric. But of course, the impacts of temperature can often depend in various different ways on the co-occurring humidity. I lost it again, there we go. So just a brief history. Models, this is still true, tend to predict global increases in specific humidity. So this is a figure from CMIP 5, but it would look the same in CMIP 6. Basically, the story here is that this whole plot is blue. It's a little less blue over the continents, but overall climate models say with climate change, everything historically and in the future should be getting more humid. You're evaporating more water from the ocean, you're diffusing that in the atmosphere, we have cloud-6-cloud-on, everything is getting more humid. Now, somewhat separately, because again, I'm kind of a heat person, I was interested, okay, maybe that's true, but how is humidity changing conditional on temperature? So if you think about, for instance, your hottest days, are they getting this like fake example that I made? If this is some past distribution of the joint distribution of temperature and humidity, and this is some present distribution, is this happening where, you're getting more humid, but even more so on the hottest days? Or you can imagine any type of behavior going on. So what we decided to do was develop a statistical model that would basically jointly model these two distributions and how they're changing with climate change. That model gave us a huge amount of information that then we couldn't even kind of process, so we are going to subset what that model gave us to look specifically at what I'm going to call hot days, or the 95th percentile of temperature, and dry days, looking at the 5th percentile of humidity, and we're going to ask ourselves how humidity is changing on those hot, dry days. So in the schematic, if I subset to my hot days and look at my low humidity days, in this schematic, I'm kind of increasing my humidity on those hot, dry days. So we ran this model on a bunch of in situ measurements. You can tell that I like in situ data in general. These are basically the only records we have of humidity, as is common with in situ data. This is obviously not a spatially uniform map, but that's what we have. We don't measure humidity very much. And this is kind of noisy, because this is station data and because of how I plotted it. Oh wait, I'll just go the other way. But the thing I want to point out is that in contrast to that first figure, that it is suspected that humidity would be increasing everywhere, what we've seen historically is not green everywhere, which would be increases, but rather in these places I'm highlighting with boxes that tend to be more of our semi-arid regions around the world, we seem to be seeing these decreases in humidity, particularly on those hot, dry days. So, as always, we wanted to understand why. To do that, we zoomed into the US just to make our problem a little bit more tractable, and focused on the southwest region, where there was particularly large decreases in humidity on those hot days. So in California and Nevada, just to give you kind of an estimate, it's already quite dry in inland California and Nevada. In some cases, these decreases in humidity were on the order of 30% of the mean state. So, taking already dry conditions and making them substantially drier. So we saw this signal in the semi-arid southwest. And the next thing, once you think about moisture, is that when it comes down to kind of a moisture budget perspective, so what's actually literally changing the moisture content in the air, there aren't that many options. And so essentially this is a complete list of the things that could change humidity in kind of over the southwest that we're exploring. And we went through and tried to understand which one of these is true. So the first is that technically an increase in precipitation can reduce humidity because you move the water from the air to the ground. But we're talking hot, dry days. It's not raining during these days. Precipitation is not super relevant. We looked vertically and determined that this was not some weird like redistribution where we're getting humidity instead moved to the upper levels of the atmosphere. And then we also looked at reanalyses and saw that we didn't really see any changes in vertically integrated horizontal moisture divergence. What all those words mean is what the atmosphere is doing in terms of pushing moisture into your domain. So we only had one option left, which was decreases in fluxes from the land surface. That's that evaporation or transpiration from plants. I also called that latent heat fluxes before. And luckily, since we'd crossed everything else off our list, that appeared to be the case. So I'll just show you that here in a few plots. What's shown in this upper plot is a map of July, August, September. This is kind of the hot, dry season in the western US. Evapotranspiration, or the water coming from the land surface, when you have years that are hot and dry. And what we saw in both the spatial pattern and also a time series sense is that there was a strong relationship between how hot and dry years were, so was it a low humidity year when it was hot, and reductions in moisture from the land surface. We then mapped those reductions in moisture from the land surface to soil moisture, so we found that soil moisture was a strong control on that moisture source from the land surface. This makes sense, especially in a very moisture-limited region like the southwestern US. And then we were able to, I can't show you one map here because it's now a bivariate model, but we basically said, okay, summertime soil moisture, we can well predict that by decreases in winter and spring soil moisture, and then summertime precipitation, which is controlling the intriannual variability. So the full causal chain basically told us that the trend is largely driven by decreases in winter and spring soil moisture that cause decreased summertime soil moisture, decreased moisture fluxes from the from the land surface, and then an increase in the probability of these low humidity days during some of our heat waves. Now, interestingly, that's kind of a self-contained project, but after that, we're thinking more and more about humidity. And this is more recent work led by my colleague Isla Simpson, where she, instead of zooming in on kind of these hot, dry days, took more of a general approach and asked, in general, do we see differences in observations versus climate models for changes in humidity on more of an annual mean basis? So remember, we saw this unexpected drying, we tried to understand why. But it turns out that this is kind of a larger scale phenomena. So what's shown here on the left are, again, some of those weather stations that have humidity, showing their annual mean trends. This is using vapor pressure. We can think about it as specific humidity or any metric of water in the air. This is looking at ERA5, which we kind of hope to trust. It's driven largely by these stations. And then what this does on the right-hand side, this is the most important plot, is this basically removes the contribution of precipitation trends to these vapor pressure trends, because we mostly view those as being caused by internal variability. And two, for both of these right-hand plots, all these places that are stipple, what that means is that the observations are basically outside the envelope of all of our CMIP6 simulations. So this is another case where our observations seem to be doing something pretty different from our climate models. And in particular, the regions that they do something different, and in particular tend to dry more, tend to be these regions of the world that are already semi-arid or already dry. So we're still trying to understand why. It would be a whole other talk of what we've learned so far about why this is happening, but just want to mention that humidity thing that we saw in the southwestern US on hot, dry days, that type of drying is actually observed in many places around the world, conditional on trends in precipitation. And we tend to not produce that same thing in climate models. There we go. Okay, so, nope. There we go. All right, so I'll just leave the summary slide up here rather than reading it to you, but I do briefly want to acknowledge our valued funding agencies, the NSF, NOAA, and the Packard Foundation who supported this work. Here's my email and my GitHub and a QR code for my website if you want to find out more. And I will take any questions in the time we have. Thank you.